So if you're given a polynomial f in k x1 to xn, and you're also given a point p alpha 1 alpha 2 all the way to alpha n that is corresponding to point x1 x2 to xn, then you can form a tangent space for this polynomial. So this is the same space you have in calculus. So this is the solution set of the following linear equation. So you take the partial with respect to x1, then plug in this point p, and then multiply it with x1 minus alpha 1. So once you plug in the point p, this will become a constant. Then you add this partial with respect to x2, again evaluate at point p, and then multiply with x2 minus alpha 2. So on till the time you go to this partial of f with respect to xn, evaluate it at point p, and multiply it with xn minus alpha n, equated equal to 0. So this is a linear equation. So the solution set of this equation, that is this value of x1 x2 all the way to xn, which satisfies this linear equation, that forms the tangent space of the polynomial. So give you an example, say f is equal to xy minus 1, so that is f is an element of kxy, and the point is given to you as alpha 1 comma alpha 2. So first you find partial with respect to x, so df by dx, and then you evaluate it at point alpha 1 alpha 2. So this is just y. So if you have it just y, you plug in this point alpha 1 alpha 2, you get alpha 2. Multiply with x1 minus alpha 1, so x minus alpha 1. So for this you have this partial, so this is just x, and then you evaluate it at point p, which is alpha 1 alpha 2, you just get alpha 1, and then x2 minus alpha 2 is y minus alpha 2 equals to 0. So this you can see is a line. Here this is a constant, this is a constant, you just have x and y. So this is a line, dimension is 1. The only problem is when you have the point 0 0. So because if you have a point 0 here and a point 0 here, then you can plug in any value of x and y. The dimension will become 2, because no matter what x you plug and what y you plug, this equation will always be satisfied if alpha 1 and alpha 2 are both 0. But we don't have a problem here, because this point 0 0 does not lie on our curve xy minus 1 equals to 0. So you can plug in x is 0 and y is 0, so you will get minus 1 here, which is not equal to 0. So this point does not lie on the curve, so we do not have a problem. Now let us do another curve gxy where we will have this problem. So everything is the same, we just have taken this constant out, so the equation would be the same. Now this is a line of dimension 1, and there is a problem only if the point is 0 0. So that is alpha 1 and alpha 2 are 0 0, and this point would lie on the curve xy equals to 0. So see, if this is 0 and this is 0, then you can plug in any value of x and y. So then the dimension will become 2. So dimension will become 2 at the origin. So at the origin the dimension will be 2. So that you can also say that both the y-axis and the x-axis are tangent to the curve at 0 0. So this problem is arising precisely because both the partials are vanishing at a point. So both partials are vanishing. So if both partials vanish, then you call the variety as singular. So if both partials vanish, we call the variety as singular. If both partials do not vanish, that at least one of them is non-zero, then you call it smooth. So here a curve will be smooth if its dimension does not jump. So here the dimension was 1 everywhere except at point 0 0. So it is 1 everywhere, and then at point 0 0, which lies on this curve xy equals to 0, you can see plug in x and y as 0 0, you will get 0 equals to 0. At point 0 0 it jumps to 2. So everywhere else it is 1, and there is a jump at origin. So a curve will be smooth if its dimension does not jump. Now if its dimension jumps, then you will call it as singular. So the proper definition is this: the dimension of the tangent space has to be equal to the dimension of your variety. So the intuitive way to remember it is that the partials, all partials should not vanish simultaneously. So now we have covered a vanishing set with one polynomial f. What if this variety is given by multiple polynomial f1, f2 all the way to fm? So here this f was going from kn to k. Obviously it's a polynomial. You feed in kn, you get k. Just like here you fed in k2. You plug in any value of x and y, you will get a single value in k. So then you just consider the Jacobian. So you will have this map now from kn to km because there are m tuples of it. Each kn would be taken to k corresponding to one f1. Then you just form your Jacobian, partial f1 by x1 all the way to f1 by xn, because all of them are going in kn. So each of these fi lies in this k, x1, x2 all the way to xn. So that's why you're taking partial all the way to xn and then down all the way to fm here. This m is same as m here. So take this Jacobian and then form the linear equations like this. So this is nothing but I've just copied the equation right here. These are same equations. Instead of f, now you have fi. So you have f1 here, f2 here, f3, f4 all the way to fm. And then you have these equations equal to 0, 0 equal to 0 equal to 0. So you just have to find the common solution of all these equations. So if you have a vanishing set like this, then for the tangent space of your vanishing set, this is nothing but this intersection of individual tangent spaces. So tangent spaces of this individual tangent spaces, their intersection. So you find the solution and the common solution. So common solution to all these equations will give you the answer. So recall the Taylor formula. So you have this equation fx1 x2 and you want to expand it at this point p alpha 1 alpha 2. Now if you forget the constant term, so there is a constant term in the expansion and you forget it, then the expansion would be something like this. You take the partial of f with respect to x1, evaluate it at point p, so this will become a constant. So this term is a constant. Then multiply it with x1 minus alpha 1. Then you have the second term, multiply it with x2 minus alpha 2, and then so on, x1 minus alpha 1 square, and so on. So you already know that this is part of the maximal ideal at point p. So we saw this in Null-Stellensatz. So this is also part of the maximal ideal at point p. Now this is x1 minus alpha 1 square. So this is part of the maximal ideal, but it is also part of the square of the maximal ideal because it is square here. Similarly here, this is part of the maximal ideal and this is part of the square of the maximal ideal. So again, both this and this are part of the maximal ideal, but then you are multiplying them. So this will be part of the square of the maximal ideal. Now if you take the maximal ideal and you modulo out the square, so if you modulo out the square, then all these terms go away. So this term will go away, this term will go away, this term will go away. So only thing remaining is this, and this looks like your tangent space. In fact, this is your tangent space. You set it equal to 0, you get your tangent space. Notice that you have this plus sign in between. You just had, if you just have like this, then you just have these two terms, but you have to have this plus sign and you have to set it equal to 0. So therefore you have to put this dual here. So tangent space is just the dual of this, mp over mp square v, where mp is the maximal ideal at point p. Now this is not a proof, this is just a intuition and hand waving argument. So in elementary algebraic geometry book by Klaus Heulich on page 104 to 106, you can find the justification and the proper proof of this. Now corollary of this result right here is that for birational varieties we have isomorphic tangent spaces. So this helps us showing when two varieties are not isomorphic. So above result is useful for showing if two varieties are not isomorphic. So for example, A1 is a smooth one-dimensional space, this is just A1, this is smooth one-dimensional space. And then you're given another polynomial f, which is x square minus y cube is equal to 0. Now you say that it is singular at point 0, 0, because if you take your partial with respect to x and then partial with respect to y, 2x minus 3y square, both of them vanish at 0 0. So both the partials are vanishing, therefore it is singular. So by this result right here, these two are not isomorphic. A1 is not isomorphic to this x square minus y cube is equal to 0. But now we will show that we can have a bijective morphism from A1 to F. So just in terms of sets you can have a bijective morphism, but they are not isomorphic as varieties. So this is important. So for example, you can construct from A1, you can go to your F. So this is point x and point y, and you can plug it in here and see it satisfies this equation. So see x square minus y cube, you plug in t3 square minus, then you have t2 cube. So this is t6, this is t6, so obviously this is 0, so satisfies this equation. In the reverse direction you obviously can go x over y. So the only problem is when y is 0, but when y is 0 you just map to 0 here. T is also taken as 0. So you have 1-to-1 correspondence, a bijective morphism. But because this curve is singular and A1 is non-singular, they are not isomorphic as varieties.